The problem with M&Ms is sitting right in front of you in this jar or in this cup or even in your hands, and it is, of course, how many M&Ms am I looking at? 4,549, but yeah, it seems like a stupid question. Of course we can give a rough estimate, or if we need an exact answer, we can literally line them up and count them one by one like I did for around an hour. It took a long time. Yet all over the world there are these jars and massive pillars filled with these things dedicated to giving you a reward if you can give the closest estimate. But people, including you, tend to be a lot worse at tasks like these. Remember, there are 4,549 M&Ms in this jar, and here's what people intuitively think without doing any math or calculations or anything like that. In your opinion, without doing any math, without using anything, how many M&Ms are in here?
I'm gonna go with 490.
1,472.
I would say maybe 4,256.
3,000.
I'm gonna say 583.
583.
Wait, 583? That's it?
Yeah.
I was thinking like way over 1,000.
But how many?
It's not that many.
Like over. No, well now I'm second guessing. I'm like 5,000.
I have no idea.
No idea is good too. So 500, but also at the same time 5,000. We're really not that good at this. In fact, right now in your head, try to picture what 100 M&Ms would look like. Really do try to visualize this. How big would that stack be? What kind of container could it fill up? Chances are the image you have in your head probably looks something like this, give or take a few. In reality though, that is 1,000 M&Ms. This is what 100 looks like. It's just a small handful. Wait, why does this happen? I mean, really, why does this happen? We spend our whole lives dealing with amounts and figures and groupings, yet our intuitive understanding for real amounts or cardinality, the number of elements in a set or grouping, is nowhere near as intuitive as we think it is. Try this with me. Here's a line segment that we'll say has length X, which can represent M&Ms, Hershey Kisses, or really whatever it is you want. Now, in your head, really do try to visualize what a segment of twice the length of length 2X would look like. Now, of course, this really isn't that hard because we're geared to handle one-dimensional scenarios like this, no problem, but now let's try to increase the dimension, giving us a square that again can represent M&Ms or any other kind of object, and this time let's try to double our area. Now, this still looks pretty normal, but doesn't it kind of sort of feel like we should have increased this by, just a bit more? I mean, yes, if we have two dimensions to work with, then doubling looks like scaling on each axis by square root of 2, which happens to be around 41%, but doesn't it feel like we just didn't really do enough? Even crazier in 3 dimensions, to get a doubling, we only need to scale up each axis by 26%, and at this point, it really does look wrong. We definitely need to add in some more volume somewhere. How can this cube be twice the volume of our original? Now, if we were 4 or even 5-dimensional creatures eating our 4 or 5-dimensional M&Ms, these perceptual distortions would continue to get worse, because then on each axis, it would look like we're scaling by the 4th root or 5th root of 2, but even in our measly 3-dimensional world, there are more problems to deal with. For example, imagine that in one hand you're holding 1 M&M and in the other you're holding 2. In other words, there's going to be a difference of 1 M&M. Well, then visually and then also tactilely, if we were to feel them, we could tell which hand has more M&Ms. Now, if we take the same scenario, but this time use 20 M&Ms and then 21 M&Ms, again, this is still a difference of only 1 M&M. Well, in this case, it gets much harder to not only feel which one has more, but also visually we can no longer tell, and that problem only gets worse and worse the more M&Ms we have. In other words, we see in terms of ratios or logarithmically, we do not see linearly. This means that no matter what M&M amount I show you, as long as I double it, you should be able to tell the difference because the ratio is still 2 to 1, but if we do like a constant offset of 1 M&M or 2 M&Ms, at that point it will become perceptually invisible. So at this point it should be clear that with our eyes and brains, we're really not equipped to tell how many M&Ms are in here just using our intuition. So the question I want to ask is how close can we get without taking a single measurement, so we can't do anything like cylindrical volume formulas or anything like this? How close can we get without taking a single measurement? I don't know the size of the M&M, the jar, how much packing density there is. How far can we take this estimate? How close can we get by using only a single photo? Let's find out. So even in a challenge like this where we only have a single image to go off of, I still think the best plan of attack is going to be a ratio of volumes. Now this might seem like a weird way to approach the problem, right? We never took a measurement. I don't even know the scale of this photo, nor the size of the M&M, the jar, anything. But if I had a big cube and filled it up with smaller cubes, in this case it's obviously an 8-to-1 ratio, you can still figure out how many cubes are inside this, even though I never gave you any kind of units for this kind of problem, right? It could have been in meters cubed, feet cubed, centimeters cubed, right? Units end up not mattering as long as we're dealing with ratios where the units are the same on the top and bottom, and we can use this exact kind of trick on this image where we don't have any kind of scale or reference or anything like that. To do this, let's exploit this jar's rotational symmetry. In other words, this thing is going to be very easy to model, and similarly, let's pick some M&M inside this jar and use similar modeling techniques to now get two models that are not necessarily to scale with the real world, but relative to each other. smaller, they're definitely to scale. So incredible, we have our 3D models, which means we can now calculate volume. Again, these numbers are going to be very big in an arbitrary unit, but if we divide relative to each other, this problem goes away and we finally get a number that is quite frankly too big. How do we account for this? Why is that number so much bigger than the initial estimate of something like 4,549? Well, the answer must be somewhere out there or somewhere out air, because we didn't account for the gaps of air that must be in between the M&Ms, right? This isn't like completely full of chocolatey goodness. No, there are packets of air and we do not know the exact packing density, especially when we have kind of random orientation and all this. So let's try to calculate that. So to calculate packing density, as you probably already expect, you take the combined area of your objects and just compare them to the area of the container that it's inside. Now, in this case of circle packing, because this is two-dimensional, so these are effectively circles, you might think that this grid or lattice type configuration is the most effective way to pack, but this is not true. It turns out that hexagonal packing or honeycomb packing is much more optimal at something like 91% when it comes to packing circles inside a two-dimensional region. Now, people have been doing these kind of packing problems or optimization problems for a long time now, right? Putting squares inside of squares or circles inside of squares, stuff like this optimally, but we don't care about this, right? We care about this random distribution kind of stuff, and we want to calculate what the packing density is in this kind of random physics-based scenario. So that's usually done via simulation, so we're just going to simulate this in 3 dimensions. In my case, instead of doing this by filling a container until it's full and then looking to see how many M&Ms were in there, I wanted to do the opposite. In other words, reshaping the container until it fits our objects, and then right before M&Ms explode out of bounds like the frame before, we call this full and then take that object to container ratio from before, which in this case gives us a calculated packing density of roughly 59.7%. So am I really saying that this jar, which looks completely filled with M&Ms, is 40% comprised of air? Yeah, and it might be hard to believe, but so is a bunch of other stuff. Remember, this cube is twice the volume of the original. We can tell the difference between 1 M&M and 2 M&Ms, but 20 and 21, no way. And don't forget that 100 M&Ms, which seems like a lot in our head, only comprises a very tiny amount of a small Ziploc bag. So yeah, it's surprising, but if we now take our calculation, right, the big jar volume that we calculated versus the tiny M&M volume that we calculated, and then multiply by this new packing density, right, accounting for the air that we shouldn't be counting in anyways, we take all these numbers and calculate them together, we get 4,458 M&Ms without taking a single measurement. Think about that for a moment. That is crazy. We got within 2% of the actual amount, not knowing the scale of the image, not taking measurements, nothing. So maybe the main takeaway is just don't trust your intuition, or maybe the main takeaway is go to your kitchen drawer, take out one of these things, a spoon, so you can scoop away your eyeballs, get rid of those things, they're useless anyways, but at least we'd be able to calculate how many eyeballs would fill up a jar, which is cool, I guess. And with that, thank you for watching. I've been CG Matter, you've been you. Bye-bye. You have no idea how long I've been waiting for this day. I've been looking at this M&M jar for a long time, making sure I don't eat any so the numbers stayed consistent and I wasn't cheating or anything, even though nobody would have noticed. But today, I finally get to eat one of these bad boys that I've been eyeing up for a long time. I'll go with the yellow. And I know this isn't the normal kind of video I usually make. I'm trying to branch out into new topics, whatever, but whatever this video was is sponsored by Skillshare. And Skillshare is an online learning community where you can learn a whole bunch of skills like photography, videography, even 3D graphics, a whole bunch of stuff that you'd probably be interested in. And on top of having a bunch of video courses, there are also online workshops, so you could work alongside digitally thousands of people that are also doing that workshop at the same time. So that could be a good motivation to keep progressing through learning whatever skill you're trying to learn. And one premium course in particular I want to recommend is how to make merch with Draplin. And by the way, Draplin is the guy who makes field notes, if you know about that. I happen to have one on me, but that's neither here or there. This course is not only about designing stuff, which is already useful, but it's also about how to repackage and how to sell to a client and stuff like this. So if you're interested in design and want to be a freelancer or something like this, I recommend watching this premium course. Now, Skillshare Premium will get you access to premium courses like this. It's also ad-free and has an annual subscription that's less than $10 a month, but I'm here to make that deal a little bit sweeter, pun intended. The first 1,000 people to click my link in the description can try a free trial of Skillshare Premium, so you can watch this course that I recommended or really anything that you want on the platform. So that link exists in the description, and I'm gonna go on to eat now 4,500, I don't even remember, many more M&Ms.